Okay, I guess we can start. Any questions? I think sometime today in the evening I'll post the grades in terms of the campus. They were pretty good, so not much to worry on that end. I just have to fix the type of the solution. So if I have time during office hours, I'll do that. If not, I'll do it once I get home. So, um, but yeah, I'll give you the information about the grade. And so today the idea was to talk about the determinant of a square matrix. Do you remember last time we talked about the determinant of a 2 by 2 matrix? Many of the properties from the 2 by 2 case just continue to work in the more general case. So what I was going to tell you what are just like the main properties for the determinant, and then how to compute it. Okay. This topic about the determinant is not one we're going to spend too much time on. So like today will be probably like the last lecture about it. Mainly we'll use it as a tool to detect whether a matrix has an inverse or not. That's like essentially the only thing we care about the determinant. So let me start by telling you that. So for us, A is an n by n matrix. And the determinant of A, that's of A. So this is a number. If you remember from last time, this number could be positive, negative, or actually also zero, that's allowed. The important thing is that geometrically, this number, if you take its absolute value, this corresponds to like some sort of volume. So in the 2 by 2 case, it is like the area of the parallelogram. In the 3 by 3 case, it would be like the volume of this box, which I think is actually called parallelepiped, or I don't know how to pronounce it, but it is like kind of that box that I drew last time. But in general, like even when the matrix is bigger than that, you cannot draw it. You cannot draw what this looks like, but it is always some sort of like hyper parallelepiped, and then like the determinant does correspond to like the volume of that. So this is some sort of volume of the box. Let's just call it box. You make that is determined by the column vectors of the matrix. And then the sign actually has to do with this thing called the orientation of the vectors, which is not something we'll spend a lot of time on, but it is like the analog of like the right-hand rule for those who have seen like the cross product and things like that. So there's like a way to like say, well, this is like the first vector, the second vector, the third vector, the fourth vector, and so on. And so if the determinant changes, has a negative sign, that means that sort of it screwed up the what we were calling like first, second, third, fourth vectors. Like it kind of reverses like how they were organized or oriented. But it's not some again, it's not something that you really have to worry too much about. Although if you watch there's like an optional video on Canvas that I posted yesterday. There were some issues I think with Canvas, but you should be able to check it out. And there's like based on a YouTube video that kind of explains a little bit more about this thing about the sign of the determinant. So if you're curious, you can watch it. But in practice, if it just comes negative, it just comes up negative. Okay. So let me tell you that these are like the important properties of the determinant. So some I tried to justify last time. Others will just say, like, as an article of faith that if it works. So the first one is that the determinant of a matrix equals that of the transpose. So it's actually that one is very useful. So determinant of A equals the determinant of A transpose. Okay. In the 2 by 2 case, we can sort of see that explicitly from the formula I had given for the determinant, but it does continue to work in general, and it's kind of miraculous from the volume perspective because the transpose kind of makes the rows into columns, and like it is a different box that you're getting when you do that, and still it is saying like that those boxes is going to have the same volume. The other formula, which is very important, is this product formula. This is like the one that actually makes the determinant like a useful quantity. And it says that if you have a product of two matrices, the determinant of the product is just a product of the determinants. Again, it is also kind of miraculous. I mean, at least geometrically, it's a little bit easier to see if you remember like the justification I did last time for areas. Kind of the same works in general, but it is kind of cool because, in particular, since these are just numbers, you can write them in any order. So this is actually also saying that the determinant of BA is the same as the determinant of AB. Okay. Because this can be like rearranged. And that's kind of, again, impressive just from the fact that, A times B is not the same as B times A, but somehow when you take their determinant, like that difference goes away and you end up getting the same answer. Okay. And from there, you get to the last property, which is very important. There are other properties I'll give you like in a couple of minutes, but right now I'm just giving you like the three that you really need to know. So the last key property is, let me use a different color. The last key property is that if the determinant of a matrix is zero, then the matrix has no inverse. That's basically the most important property for us of the determinant. So the determinant of A equals zero, A has no inverse. And there's kind of like a converse to that, which is very useful, which is that if the determinant is not zero, then the matrix happens to have an inverse. So it's like it gives you like full information about the inverse of a matrix. So if the determinant is a non-zero number, A inverse exists. And from this product formula, if you remember, you can actually find like a formula for the inverse of the matrix, or like a formula for the determinant of the inverse, because the determinant of A inverse is just going to be 1 over the determinant of A. Okay. So from that perspective, the determinant is kind of like the perfect detection tool if you want to know whether an inverse exists or not. You just compute a determinant. If it gives you 0, there's no inverse. If it gives you something non-zero, there is an inverse. Okay, is that making sense? Any questions? So again, those are the three main properties. Now what I have to tell you is how to compute the determinant in the general case. And this, like, like going through this formula would take us forever. So like, I'll just give you the formula and we'll take it as, again, like a black box that it actually works. So let me give you the formula for the determinant. So remember in the 2 by 2 case, what was the determinant of A, B, C, D? Yeah, you just multiply the main diagonal, that's how it's called. Then multiply the other diagonal, which is BC, and then you just subtract the answers. Okay. So it's fairly straightforward. So that's the determinant for the 2 by 2 case. And now we can talk about the 3 by 3 case. I'm going to give you a second to write this down. The cool thing about this formula for computing the determinant is that kind of it gives you the formula in terms of determinants of smaller matrices. So in this case, the formula of this 3 by 3 matrix for the determinant will be given in terms of 2 by 2 matrices or determinants of 2 by 2 matrices. And what will happen, you'll see like in the 4 by 4 case, the formula for the determinant of 4 by 4 will be given in terms of determinants of 3 by 3. And then you can find the determinants of those 3 by 3 in terms of 2 by 2s. So it's kind of like, you always can bring it, lower it down to the 2 by 2 case and you get like the answer. So again, it's kind of like black box that it works. Let me give you like to memorize it, it is not too bad. You just have to do the following. So for this 3 by 3, like what you will do is like associate to this matrix like a table of signs or a matrix of signs. Let me put it below here. So what do I mean by that? Well, this is 3 by 3. I'll put like a 3 by 3 matrix here. And the idea is that in this matrix, you always start with a plus. Okay. And from there, you just alternate between plus or minus. So it's like plus, minus, plus, right? You are alternating. And then plus, minus, plus, then minus, plus, minus, and then plus, minus, plus, right? So if this were like red and black, I think that would be like a checkers board or whatever this name is called, right? Like it's just like a board that you color with 2 different colors and it just switches back and forth. The only convention, like to remember this, is that it always starts with a plus on the upper left corner, and once you remember this and that if you switch it, then more or less everything else is determined. Okay, and now comes the cool thing that you, let me see which one will be useful for this. Okay, so I want to compute the determinant of this 3 by 3, and for that, I have to choose my favorite row or column of the matrix. So someone wants to give me their favorite row or column. What would be another? Okay, these are volunteers. Just choose one. You want, okay, so let's go through row 1. Good. So since I'm choosing row 1, I'll choose row 1 in the matrix of signs or the sign matrix. Okay. And now it's very easy. What I'm going to do is like kind of read these coefficients, these entries from the matrix, but I'll read them with the corresponding sign that the formula is giving me. So A comes with a plus, right? So I'll put plus A. Okay, and the idea is that I'll multiply this times a determinant. You'll see what I put here in a second. But so this will be plus A minus B, right? Because now the B goes with a minus. And I'll put a determinant here as well. And then plus C again, right? So if you look at it, it's again plus A minus B plus C, and then the choices of signs are coming from the this matrix of signs. Okay. And how do you fill this in? The idea is that we're going to put here compute determinants of 2x2 matrices. Which 2x2 matrices? The ones that we get by deleting the corresponding row and column of which of the entry we extracted. So for example, when we extract the coefficient A, right? Coefficient A is in row 1, column 1. So you have to delete row 1, column 1 from the matrix. And if you look at it, like you get like a 2x2 mini matrix here. Right? What are the entries of this 2x2? Is like E, F, H, I. Does that make sense? And the same will go for the others. So for example, for the P, it's like row 1, column 2. So imagine deleting row 1, column, like you kind of do it in your brain, right? Like you don't have to write this down in your solution, but you imagine deleting row 1, column 2. So which entry do we see? D, F, G, I, right? And for C, you delete row 1, column 3, and you see again like a 2x2 matrix, and you put D, E, G, H. That makes sense. And that's it in the sense that there you just have to multiply, compute some mini determinants and do all of this arithmetic, but that will be the answer. So let me give you an example so that we see how this looks like. So imagine that I wanted to compute the following. Okay, so we have this 3x3 matrix, and I wanted to find the determinant of this 3x3 matrix. And if you look at the formula, right, is plus 1 times the determinant minus 2 times the determinant plus 0 times the determinant, right? And then, well, what we would have to do next is to fill this in. Is that making sense? Obviously, in practice, like one that has like the 0, you wouldn't even need to write it because 0 times anything will become 0. But I'm just writing everything down explicitly so that you see the answer. Yeah. Mm-hmm. Right. What you have to look at is that the like for example, this could have been 0, right? What we care about is like the combination of these quantities. So we need the combination of all of these to be non-zero. It doesn't matter if the individual factors are 0 or not, if that makes sense. Yeah. So it's just the like total number that we care about for figuring out if there's an inverse. So it's okay if like the individual 2x2 matrices like the mini matrices could have determinant 0 or not, and that's fine. But yeah, good question. Any other questions so far? Is the setup making sense? So now we just start deleting. So right, I was the first row, first column, you delete that, you get 0, 7, 4, 5, right? Then you delete the first row, second column, you get 9, 7, 2, 5. And finally, you delete first row, third column, you get 9, 0, 2, 4. Is that making sense? And now it's just like, as you can see, many things in this course of linear algebra is just like doing a bunch of sums and products. So you just have to make sure that you don't make any typos. But after this, like it has been reduced to doing a lot of multiplications. So you don't have to write the one, but if you want, we can put it just for now. So this gets 0 times 5 is 0, minus 4 times 7 is minus 28, right? Then negative 2, then 9 times 5 is 45, minus 2 times 7, what is 14. And well, obviously we don't care about the last one because it's just 0, but if you want, I'll just write it for you. 0 times 36, right? That's the last determinant. Like 36 minus 0, so to be super precise. So now you get negative 28. So this one, what does it give you? 45 minus 14, what's that? 31? 31 times 2 is 62, right? And this one is 0. And negative 28 minus 62, that's negative 90, right? So the determinant of this 3 by 3 matrix should be negative 90. And again, from the perspective of like, if I ask you whether this has an inverse or not, you would say it has an inverse because this number was not 0, right? So now you don't need to go through like what you did before, where you had to comment this to the identity and try to reduce it to see whether you could get like the identity on the left-hand side, if you remember this method that we use for finding an inverse. Is that making sense? The first bit. Let me give you a second to calculate this. Okay, now the cool thing is that there was nothing special about row 1. So you could have chosen a different row or column, and the answer would still be the same. So which row or column would we choose? Anyone wants to give me another option? Yeah, column 3. You say column 3. What would you want to say?
One with zeros.
Right, like as you can see, like it is a good strategy to at least choose a row or column with at least some zeros, right? Because that would just kill a bunch of things. So, like for example, we could have gone with column 3, right? Because there's a 0 here. Also column 2 because there's a 0 here, or even row 2, right? Because there's a 0 here. So just because we already did a row, let me use one with a column, and I'll do column 2 because that way we'll start with a negative sign so that you see like how this looks like. But right, like now you start getting like a sense for like strategies, and the strategy is kind of like to choose a row or column with the most number of zeros. So like the most number of zeros in this case was 1, but if there had been like a row with 2 zeros or a column with 2 zeros, then we would definitely have used that one. Okay, so let me just let's compute the same determinant using column 2. For 5. Okay. And again, if you compare with the matrix of signs, now we're going to use this column, right? So we'll start with a minus. It was going to be minus plus minus. So it's minus 2 times the determinant plus 0 times the determinant minus 4 times the determinant. Okay. sense. And now we do exactly the same. So for these two, we have to remove the row and column to which it belongs. So you remove first row, second column. When you do that, you get 9, 7, 2, 5, right? For the 0, you have to remove second row, second column. So you get 1, 0, 2, 5. And for the 4, you have to remove second column, third row. So you get 1, 0, 9, 7. That making sense? And then like the setup, I mean, the kind of getting the setup right is like the big thing, because after that it's just like computing a bunch of determinants. So this is -2. What is the determinant? 9 times 5 is 45. Minus 14. Okay, we saw this one before. I don't care about this one because it's just 0. So let's just put plus 0. Minus 4. 7 minus 0, right? And well, it kind of looks that clear that it will give us the same answer, but it for different reasons, right? Because we're doing different multiplications. So it is this is still 31, and 31 times -2 is minus 62. And then this one is minus 28, right? But you see, like the way we're getting, like, for example, 28 is different from before and things like that. So this still gives you -9. Is that okay? And it doesn't matter which row or which column you would have used, it will always give you the same answer. Okay. Of course, like in practice, you do try to use rows or columns with zeros, just to make your life easier. Any questions? So, all the other cases, it's essentially the same idea, as you can imagine. So let's do a one of 4 by 4, just to pin this down. But after that, like you can imagine, like 6 by 6, how it would work, 5 by 5. It's essentially, it's always the same. It's just that it's not worth like too much time. Like you can see, just doing like a bunch of multiplications at the end of the day. So like finding the determinant is like it's useful to know what you're getting out of it, but it's not like it's just like a long computation. It doesn't like the computation itself is not worth spending too much time on doing like many examples, because they kind of always work the same way. I mean, you can go to Wolfram alpha and type determinant, and, enter the entries, and you get it in less than 1 second, like the formula. So it's like finding the determinant is not such a big thing. It's more like what are we getting out of it that is important to understand. So how would we find this? Let's say I wanted to find the determinant of this 4 by 4 matrix. So again, the first thing you'll do is to draw this matrix of signs. So you can put it here, plus, minus, plus, minus, plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. Okay. And then you just choose your favorite row or column. Again, they're kind of nice net candidates here because some rows or columns have like 2 zeros, right? So which one do you want to use?
First one,
So first row or first column?
first row.
Okay, so that could work, but actually I want to use a different one. I'll just say in a second what. Last row? Okay, so if you look do the last row, the thing that will happen is that once you get to this one, you'll see this matrix, right? And that's the one we were doing in this example. So I kind of set it up so that we could like use the answer from before, so to save us a couple of minutes, right? So it's kind of like a trick. Otherwise, it would be totally fine to use any row or column. So, but yeah, let's do like the last row. If you do the last row, again, you compare to the last row in the matrix of signs. Right? And this gives you what? It gives you -1 times the determinant, right? Plus 0 times the determinant. -0 times the determinant. Plus 5 times the determinant. Okay. But the point is that the determinants you put here are of 3x3 matrices, right? So that's how you keep kind of like reducing the size of the problem. So what do we put here? Like the 3x3 matrix that you see by deleting the row and column to which this one belongs to get you 2, 0, 0, 0, 7, 0, 4, 5, 6. Okay. Then for the second 0, you delete the row or column for this one. So you get 1, 9, 2, 0, 7, 5. 006. If there's any typos, let me know. I mean, it wouldn't matter too much here because there's a 0, but it's just kind of useful to get the formula right. And then for this one, delete the row and column for this third 0. So you get 192, 204, then 006 again. For the last one, again, if you delete the row and column for this one, you see the 3x3 matrix from the previous example. Isn't making sense? Okay, so these two won't make a difference. And again, this one would just be -90. That was a previous calculation. Okay, and then for this one, you see a 3x3 matrix, and again, we have to decide how to compute it. So you choose your favorite row or column. So which one can we choose? Which one? Yeah. Yeah, we can use the first row again because there's 2 zeros on the first row, so that's kind of useful. So what does this answer start looking like? So it would be -1 times what? This determinant would be 2 times the determinant of like what you get by deleting the row and column. So if you delete the row and column, you get 7, 0, 5, 6. And again, the others don't really matter, but I'll still write them down. So 0, 0, 4, 6. And the last one is plus 0, 7, 4, 5. So that's how the first like looks like, and then you get plus 0, so that doesn't matter. That's fine. And then plus 5 times -90 because that was the last example. Okay. So you get -1, 7 times 6 is 42, right? 42, and there's a 2 in front here. So it becomes -84. Right. And then minus 450. There's anything. And the total answer comes to be negative 534. So notice, like, even though none of the entries of the matrix were particularly large, still the answer is relatively big. So don't be surprised if sometimes like the number is kind of high. Again, this said that if you look at the absolute value of that number is 534. So the volume, folks, the hyper volume, there's like a hyper box you could make out of like these 4 vectors. And the volume of that would be 534 in whatever units you're using, right? I mean, this would be like meters to the 4, or like, because it's really there, it would be 1 unit of length per each column, so it has units of length to the 4. So that's why it's like hyper volume. And then more importantly for us would be that this number is not 0. So because it's not 0, that would have an inverse if you were trying to compute the inverse. Okay. So again, if you watch the video for the optional quiz, you'll see like a nice illustration of what does it mean for the negative, for the sign to be negative. It's kind of like you're changing, again, like your mind on what is like right-handed versus left-handed. At least that's one way to think about it. Okay. And every other case of the determinant is more or less the same. Like there's no much to it, like in terms of computations. Okay, any questions about this? So the typical determinant question is like, well, I give you a matrix and I ask you, is it matrix invariable? And then you just find it's a determinant. That's more or less how we want to use it. Oh, submersibility. So now the idea is that I already gave you like the important formulas for the determinant. Let me just give you some more, which are still kind of useful to know, to keep in mind. But they're not as crucial as the ones that I started with at the beginning. But it's still kind of nice to know what they say. So let me write that down here. So other formulas of the determinant. So the first two are kind of maybe clear. Kind of useful to know anyway. The determinant of a 0 matrix is just 0, right? Like the one whose every entry is 0. And the determinant of the identity matrix is 1. Okay. That's kind of nice to know. There's also like a convenient formula for the upper triangular or lower triangular matrices. So I haven't spent too much time talking about those, but let me tell you now what they are. So this says that the determinant of an upper or lower triangular matrix is is just the product of the diagonal. And I'll say what I mean by this. So what do I mean by this? So for example, let's look at this matrix. So if you look at this matrix, there's like some sort of triangle here, right? And everything outside that triangle is a bunch of zeros, right? So this matrix is called like upper triangular. And the idea is that the determinant for a matrix of this form would just be the product of the elements along the diagonal. So the main diagonal is 1 to 4. So the determinant here would be 1 times 2 times 4, which is 8. Okay. In practice, it's not wouldn't be too hard to find on your own because there are a bunch of zeros in an upper triangular matrix. So you could just have used like the formula for expanding the determinant along the first column, for example. But it's still nice to know that you can just multiply the elements of the diagonal. Let me give you another example. So if I give you okay, so if you look at a matrix like this, so everything outside this triangle is a bunch of zeros, right? Now this one is called lower triangular because like the non-zero entries are below the diagonal, basically, or they only happen below the diagonal. The formula for the determinant in this case is the same. You just multiply the elements along the diagonal. So it would be 2 times 0 times 3 times 4. The important thing here is that there was a 0, right, in one of the diagonals. So that kind of gets rid of everything else. So this matrix would be 0. The determinant for this matrix would be 0. And that would tell you, for example, that this matrix does not have an inverse immediately. So there's no point in trying to reduce this to the identity or whatever, like you would fail to do so. You would fail to find an inverse. Is that making sense? So it is this one is kind of convenient to remember. So yeah, this one does make sense to keep in mind. The other thing that's kind of nice to know is how this formula interacts with the operations we study for reducing a matrix. So what do I mean by that? So there were 3 row operations we did for reducing a matrix. One of them was like to exchange rows, if you remember, right? So The formula for the determinant says that when you exchange rows, the determinant changes sign. So let me write that down. So what do I mean? What do I mean by this? So suppose I give you the 3 by 3 matrix, and for some silly reason, you just want to change rows to with rows 3. Like you just want to exchange those two. Those are the two that I'm changing. So what the formula says is that the determinants are not equal, they just differ by a sign. Yeah. So the thing is like this sign refers to the overall determinant, right? So like I'm saying, like for example, this the determinant of this 3 by 3 happened to be 5. The determinant for the original one would be -5, right? So it's not that you're changing anything to like right. You have to think about it in terms of the total thing. Like for example, like you could decide to change row 1 now with row 3 if you wanted. Right, so let's say I wanted to change row 1 with row 3. So it becomes now 0, 4, 5, right? -2, 3, 4, 1, 2, 3. So because I changed, there was a minus a minus sign from before, but now because I made another change, I get another minus sign. So they kind of cancel one another, right? So these two cancel out, and this actually ends up having the same value as the original. Because minus minus gives you plus. That makes sense. That happens if you think about it from the geometric formula, because again, the determinant also keeps track of like what you're calling the first, second, third vectors in a sense. So when you change two vectors, you're kind of reversing what you mean by the orientation, whatever that is. And then when you change it again, you kind of are undoing the effect of reversing the orientation. That's one way to think about it. It is similar to like an operation, you know, like think of it as similar to being like right-handed versus left-handed. So like changing two rows turns like a right-handed person into a left-handed person. And you change your rows again, you just return to your original form. It is kind of like that. Or switching an even number into an odd number somehow, and then doing the row operation like turns it back to a second time, makes it even. Is that okay? So that's what it's kind of, again, it's kind of cool to see that this is true. Another operation that we had when we were reducing a matrix was kind of multiplying a row by a number or dividing a row by a number. So there's a similar effect on on the determinant, which actually I kind of wrote last time, but I didn't write it this way. But the property is that if there's a number that appears on every entry of the determinant, on every row, like, let me write it, because it will. So if a number if a number appears on every element of a row of one row of the matrix, you can take it outside the determinant. And you'll see what I mean by this. It's out of the outside the determinant. So what I mean by this is that so if you look at this matrix, there's sort of like square root of 2, right? On every entry of the third row. So what this formula says is that you can kind of take out this root of 2 outside the determinant. So this will give you root of 2 times the determinant of 1, 2, 3, 0, 5. Yeah.
For a column here.
It would, because it's kind of a bit of a cheat, but because the determinant of A equals the same of the transpose, that kind of means that there's like analogous property for the columns as well. So for example, I didn't say it, but you know, if you had decided to switch the columns, you also gain like a sign, because again, the fact that the determinant is the same as the transpose means that the operation doesn't matter if you do them on rows or columns. So yeah, if the third column had all been multiplied by root of 2, you can also pull that out. Is that making sense? I'm just writing it in terms of row operations because that's kind of more closely related to how we were reducing a matrix. But yeah, because of this property with the transpose, there's also an analogous property for the columns. Yeah, but good point. Anyone else? So if every entry had been multiplied by root of 2, right? What should I put here? What would I have put here if I wanted to pull it out? Right, it's root of 2 cubed. Like the idea is that you get like a root of 2 per row, right? So if this had appeared like like in the first and second rows as well, you get like a root of 2 per row. Like the important thing here is like there's enough, you get like a factorize, you can factorize for each row. That's what I'm trying to say. So the effect accumulates. That makes sense because remember, again, if you think of, this is how I explained it last time in terms of areas, think of this as some sort of volume, right? So it's like saying you're making the width root of 2 times bigger, right? So the volume should just be root of 2 times the original one. But so if you make the width, the base, and the height root of 2 times bigger each, like the total volume should rescale by a root of 2 cubed. So the rescaling, it is essentially this rescaling property that I had mentioned before, last class, said in a slightly different way. Okay. But it is important to just notice that the rescaling is for each row. So if everything had like a root of 2, you would have obtained like root of 2 cubed. Or if 2 rows had root of 2, then you get root of 2 squared, right? But it's 1 per row. This is analogous to like for, hopefully most of you have taken calculus. But it is like an analogous property, like if you have like the derivative of 3x squared, this is like 3, the derivative of x squared, right? And you can pull out constants out of a derivative, like you can sort of pull out constants out of like, I mean, the determinant is just like one constant per row. That's kind of how you should think about it. Does that make sense? Okay. That also tells you immediately that if you have a row with a bunch of zeros, right? Like the determinant should be 0, right? Because you're kind of taking it out, and you get 0 times anything. So I mean that's also clear if you had just expanded along that row. There's many ways to see this, but and good. The last property, so this is switching rows. This is like the analog of multiplying a row by a number. You should think about it that way. What was the last operation when we were reducing a matrix that we would use? Right, like we had this combination of rows, right? And the cool thing is that the determinant is kind of blind to it. So the determinant, when you add rows, gives you the same answer. So when adding or subtracting rows, however you want to think about it, adding rows preserves a determinant. So for example, if you look at the original matrix that we were using for these things, 1, 2, 3, 0, 4, 5, and -2, 3, 4. Right, if you were in the mode of reducing this matrix, right, the next thing that you would have done to reduce this matrix is to put a 0 here, right? To put a 0 here, you would have done something like 2 row 1 plus row 3, right? Into row 3. And the property of the determinant is that actually preserves the determinant. That one is kind of weird. I mean, it's not so clear why it works, but it actually does working. So when you do this operation, you get 2, you get 0, 4 with 3 is 7, and 6 with 4 is 10. Yeah. Oh no, it's because right, it's kind of like right, it's it doesn't, the fact that there was, because it's like kind of row 1 plus row 1 plus row 3. So like the important thing is like kind of like the addition reserves the determinant. So after that, it's just like doesn't matter how many times you multiply. Okay, again, like why does addition preserve the determinant? It's kind of like a big mystery. But once you think that that's true, doing this is kind of like the same as having done like row 1 plus row 1 plus row 3. So but this one is maybe more clear why it would be useful, because this is actually like a good operation to start creating zeros, right? So it is easier to find this determinant versus this one because now this first column has 2 zeros, right? So in fact, you could do it in a single step, right? This, like if you expand along the first column, it will be 1 times the determinant of 4, 5, 7, 10, right? And then this is 40 minus what? 35? I think it's 5. Which would have taken us a little bit more time if you had done it from this version, because you would have computed like two non-zero determinants. So of course, like in practice, again, if you don't gain, for these special cases where it's like 3 by 3 or 4 by 4, you don't gain that much by doing this in terms of time. But if you had like a 10 by 10 matrix, then you can imagine what it would be useful to create first a bunch of zeros using row operations, because it just will reduce your time it will reduce your time eventually. So, if we were in the business of like speeding up determinant computations, it would be a useful rule. But again, in practice, it's just more interested in that you understand like the basic formula for the determinant. But it's not like my intent to give you like a Titanic matrix that require like a bunch of like clever tricks to find it. Okay. So this is more or less like what I had to say about how to find the determinant of a matrix. So let's see. We're finishing a little bit early, but things like next topic it is okay. We just talked about determinants. In terms of difficulty for the course, like in terms of a roller coaster, the next topic is the peak of the course. So the next topic is like I think what corresponds to like chapter 4 on the book, if you're following the book, which is like this thing about subspaces of a vector space. So that it is a bit tricky, so I have to take it slow. But it doesn't make a lot of sense to like start right now because it is completely different from what we're saying. Okay, so yeah, maybe you feel free to just end a little bit early today. But as I said, I'll post I'll send an announcement probably in the evening telling you your grades, but they were pretty good. And then on Wednesday we'll start like again will be probably the hardest topic of the entire semester, like which is just like subspaces of a matrix. And so yeah, just keep an eye on this one. But yeah, I'll see you on Wednesday unless there are any questions. I don't really want to.